morning, students. So, in continuation to the previous one, the heat transfer in the metal bar, which previously has been solved for temperature boundary conditions, now that we will solve for convective boundary conditions. So, in this case, we know the convective heat transfer coefficients at the boundaries so that the heat transfer can take place from the boundaries. So here we can balance here the conductive flux at left hand side boundary equal to the convective flux. Same thing, conductive flux at the right hand side boundary equal to the corresponding convective flux. Now these boundaries also need to be discretized using finite difference expressions to get the expressions of T0 and Tn plus 1, and then these T0 and Tn plus 1 can be substituted back into your equation 5, which we have long time back somewhere here. This was the, you can see equation 5, which need to be solved for this second order differential equations for temperature. So in this case, so you have this T0 and T1. Now these T0 can be substituted in the expanded form and can be arranged into the matrix form, and finally you can solve it. So to discretize equation 6 and 7, so we can write this one. So this is the central difference formula for first order derivative, and then they need to resolve here, substitute here I equal to 1. So we substitute I equal to 1, we will get this equation. We can rearrange that, so we will get T0, expression for T0 from here. So this is the temperature at left hand side boundary. Now for the equation 7, means these equations need to be discretized again at I equal to n. So if you discuss substitute I equal to n here, so we will get this equation. So we will get expression here for n plus 1. Now we have the expression for T0 from 2.3. We can substitute here into the equation 6 here, this one. So we substitute here this one. So we have this equation finally. So this is equation 7. So if we substitute that to equation 2.4 as well to calculate n1, so we got the n1 here. Now substituting this into the equation 6 T0, finally we'll get this equation here by arranging them, and now we can rearrange them, and finally this is the boundary temperature actually. So this is practically the expression for T0. This is the second element, T2 coefficient. Now we can substitute n plus 1 into the equation 5, which we have written the long time back at I equal to n. So we can rearrange that, we can get this, finally we can rearrange this. So this is your equation here. This practically temperature is Tn plus 1. So this is the boundary temperature again. So we will write in the matrix format here. So we will compare previous matrix A1 with this A2. So here you see these elements, this one, all diagonal elements are same. Off diagonal is also same, this one. This is also same. Only thing, this here, this one has been changed in the first row, second element, and last row, second element actually. So these two have been changed due to the boundary conditions. These need some incorporation from convective heat transfer flux. So this is the boundary condition here, boundary condition the matrix. So in this boundary condition matrix, you are getting this is the temperature at the left hand side boundary. This is the temperature on the right hand side boundary, and it will due to the that convective flux is there. Now same way the matrix can be regenerated again. The commands are same as we did for previous matrix A1. This is just to generate the element, first element A211. Then this is again to generate its second element. This is in only in the first row. Then this is the two commands just to generate in between elements. Then after that we can calculate here for the last row only one element, the second last element of the last row, and then this is again B11, so we can calculate here the first element here for this, practically B12 actually. So we can calculate this one and then again this one. So this is boundary condition matrix. So practically on first element and this is the last element. So this is again the same guidelines. We can write the MATLAB code in the same commands by changing the simple expressions. This is the values here. So here the length was taken 0.4 meter, conductivity was taken 2.3, area 20, and temperature 80, heat transfer coefficient on the left hand side 30 watt per meter square per degree Celsius. Then right hand side temperature of surrounding air was 15 degrees Celsius and heat transfer coefficient was considered 24 watt per meter square per degree Celsius. So these were assumed that constant thermal conductivity, no heat generation, steady state, one-dimensional heat transfer only. So this is the analytical expression as we already have. So this is just to calculate temperature again. So this is Q and this is the analytically calculated value of heat transfer rate. So this is the graph which says the temperature as a function of distance. So this is what we have here. So temperature is easy to formulate. Only thing is change your discretize here the boundary conditions. Also that is the flux boundary condition just to get the expression of T0, and that T0 was substituted back into the resultant equations for the second order temperature differential equations, and finally we end up with the results. So in next class we will continue for heat transfer in the cylindrical coordinate.